Thank you very much, Giovanni, and all the organisers for the chance to speak to you all today. I can see really quite a large number of people here, so this very successful idea to have these seminars. So yeah, as Giovanni has said, I want to talk to you today. I'm very pleased to have the chance to talk about the work we've done in the last few years looking at skyrmions in chiral magnetic multilayers. And I'm just going to start actually by acknowledging all the people who did the work, and particularly a couple of people here have got their names underlined. Right, let me just see if I can get this laser pointer thing working. Can you see my little red dot moving? Anyone? Maybe not. Okay, anyway. All right, great. So those, so in particular, Katerina Zeisler and Simone Finizio, who were both postdocs funded by this Magic Sky FET project, did a lot of the work you're about to see today. Katerina was based in Leeds with me, and Simone is still at the Paul Scherrer Institute at Swiss Light Source, and we used their scanning transmission X-ray microscope Pollux to look at our samples. But as you can see, lots of other people have contributed along the way, and we've had funding from various different places. And even now, I'm happy to still be able to put this flag on my slides. Chiral magnetic skyrmions are spin textures. They have a special topology and they have sort of particle-like properties. And the idea of skyrmions is derived from Tony Skyrm. There's a picture of him down here. He wasn't remotely interested in magnetism, actually. He was interested in the stability of fields of particles in high energy physics in sort of quantum field theory. And his idea was that if I sort of make a topological defect in this quantum field, then it can't be just like a wave that can dissipate away. Its topology will stabilize it. I think it's fair to say that idea had not really caught on in particle physics in the mainstream anyway. But it turned out that the sort of mathematical concepts he developed were enormously useful actually in condensed matter physics, and they've been used to study the quantum Hall effect. They're used in liquid crystals, and in the last decade or so, as I'm sure many of you know, there's been a huge amount of interest in skyrmions in magnetism. So this is an example of what the skyrmion might look like. So you can see it's a circular object here, and all around its rim, the magnetization points up, and in the center, there's a point where the magnetization points down. And then the other spins all sort of swirl around this. And what's important about this thing is that if you look at it, you can find somewhere inside it a spin that points in any direction in space. And so one way to kind of generate this thing actually is you start off with this sphere in block space, in spin space. So we've got spins here pointing, completely covering this sphere, pointing in every direction. Then to generate this type of skyrmion, which is called a block skyrmion, you sort of need to take your hedgehog and kind of comb it around the middle, but we still have spins pointing in every direction in space. And then you project this down, so the south pole of the sphere becomes the center, and the north pole becomes the rim of this thing. So if you're more mathematically inclined, then what you can do is define this winding number, which is given by this formula up here. And if you calculate this winding number for a spin texture like this, then you'll come back with a value of 1. Whereas if, for a uniform magnetization, for instance, you get back 0. And this really captures one of these key ideas of topology, which is that when you change from one topology to another, it's really a discrete transition. So this thing cannot be smoothly deformed back to a uniform state, and that's what stabilizes it. Also, as you can see, it has spins pointing all in the same direction around its edge. So you can embed that in a ferromagnetic material, and it can move around as a sort of particle-like object. And these particles can crystallize. This is one of the first direct observations of magnetic skyrmions in this compound iron cobalt silicon. This is a Lorentz micrograph from the Ricken group, and you can see that these things sort of hexagonally close pack. And then there's a very interesting emergent electrodynamics that comes from all of this. Up here we've got another FRS. This is Sir Michael Berry, who came up with the concept of a Berry phase. And if we think about Berry phases in this system, then as an electron, a conduction electron passes through this spin texture, then its spin has to track the local magnetization, and it will twirl around like this. And it will accumulate Berry phase as it does so. Now, if you're a sort of simple person like me, you would say, well, this is all very complicated. I don't really understand these Berry phases, but I do know what the Aharonov-Bohm effect is. And so what I can do is pretend that this phase that the wave function has accumulated has come from an Aharonov-Bohm mechanism, and that means the electron must have seen some magnetic field. So we invent this fictitious magnetic flux to do the bookkeeping to account for this Berry phase, and it turns out that this is quite a useful way of thinking in Skyrmion physics, because it turns out that each Skyrmion gives you phi naught, the flux quantum of this fictitious magnetic flux. So then you can sort of count these Skyrmions and work out their areal density, and that will give you an effective magnetic flux density. And it turns out that although that's a mathematical fiction, it still gives you a Lorentz force. So the electrons really are deflected, and that gives rise to a Hall voltage that you can measure. And this is called the topological Hall effect, which we'll come to later on. So that's what Skyrmions are. The systems that I'm going to talk about today, where we've been studying our Skyrmions, are like this. They're these multilayers. This is a TEM cross-section of one and a schematic where we have these very thin magnetic layers, just under nanometer thickness, typically. And we put heavy metals around them, and you have different heavy metals above and below, and that gives you a Dzyaloshinski-Maria interaction, which makes the magnetism chiral. It wants to rotate in a particular direction. So these ferromagnets have to be very thin because that DMI is generated at the interfaces. So you need their properties to be dominated by the interfaces rather than the bulk. The other thing that they do is they give you an out-of-plane magnetic anisotropy. So here are some polar Kerr loops for some multi-layers with different numbers of repeats. And you can see that they're nice and square, and that means that we have magnetization out of the plane. And here are some Lorentz micrographs that were taken actually at Brookhaven National Lab, just on a sheet film of one of these samples. And we've coloured them in blue and red to give you false colours for magnetization pointing in and out of the screen. The actual Lorentz contrast is the bright and dark lines around the edges. And what you can see is you get these kind of very typical sort of dendritic domains that you often get in these out-of-plane materials. But you can see little objects here and there that are detached from them, like there, maybe here. If you zoom right in on one of those, you can find these little circular things where there's a reverse magnetization in the middle. And so that's a magnetic Skyrmion, and it's sitting there isolated in a ferromagnetic background. This should give you a scale bar. The diameter of this thing is about 150, 200 nanometers in this case. There's lots of appealing concepts to do with topology and Berry phases and lots of interesting physics in these things. But the other reason that Skyrmions have really taken off is that there are lots of ideas for using them in various kinds of future computing technologies. So because of the fact that they're small and they're stabilized by their topology, and they are actually can be moved around using spin torques, especially spin orbit torques. They're appealing as a way of representing digital data in spintronic devices. And something that you see a lot is sort of proposals for kind of racetracks where you could write and read Skyrmions and make them sort of travel up and down the racetrack, representing a stream of data. But you can also, there are proposals for doing Boolean logic with these things. and also proposals for doing kind of neuromorphic type computing. And I think actually this slide probably needs updating, because this proposal has actually been built in Matthias Klauwe's group, and they've shown that it works. But nevertheless, even though the racetrack may perhaps not ever turn out to be especially useful as a technology, it is quite useful for us thinking about the things you would need to do in order to turn Skyrmion structures into something that could be a technology. You would need to be able to write data, so you need to be able to nucleate Skyrmions, and you need to be able to manipulate that data, so you need to be able to propagate them around, and you need to be able to read that data back, so you need to be able to detect them somehow. And you'd like ideally to do all those things by electrical means. So I'm going to show you some experiments we've done where we've done all of these things. So let's start with nucleation. So how to create a Skyrmion. So this is the device that we've studied, and the magnetic part is this rectangle in the middle. So this is a wire made of platinum, cobalt, boron, iridium multilayer. And it's 2 microns wide, and it's got electrical contacts at either end. So there's just a sort of flat drain contact here. This contact, as you can see, has been shaped into a point. And then lying on top of the wire is this other piece of copper, which we call an omega coil. That's electrically isolated from the wire. And it's shaped so that you can put a current pulse through that, and it will generate a field that will saturate the magnetization in this central region, and give you back a uniform state. So this is all connected up with high bandwidth probes, and it's also built on a nitride membrane so that it can go into the transmission X-ray microscope at the Swiss light source. And then these are the kind of data that we got. So this is an example here of 3 micrographs where we've got uniform contrast, so just a uniformly magnetized wire. And then we can put a current pulse in through this tip, and because of the shape of that contact, it generates a very high current density just at the tip. And after we've done that, you can take an image, and there's a Skyrmion, this patch of dark contrast. And then we can delete that again using our omega coil. And so we've kind of made this phase diagram where we've investigated what happens for pulses with different current densities and different pulse lengths that we've injected this nucleation pulse. And what you can see is for pulses that are too short or too weak, nothing happens. The wire stays uniformly magnetized. And if you get a bit too over enthusiastic and the pulse is too long or too intense, then you end up with some very complicated multi-domain pattern, because you've basically heated your wire up too much. But there's this band across the middle with these cyan points where we can obtain a single Skyrmion. And it's worth pointing out a couple of things. This is all done at 0 field, and also it's very deterministic. So when you're in this cyan band, then basically you press a button and you send in your current pulse, and you always get 1 Skyrmion. It turns out the size of the Skyrmion actually depends on the kind of pulse you use. So we've plotted here the Skyrmion area against the injected charge. It's just the integral of the current pulse, and you can see we get these straight lines. So basically the current pulse creates this Skyrmion and starts to inflate it, and then it kind of sticks at the size that when the pulse ends. Okay, what I want to show you now is how we've studied Skyrmions moving. And although actually I was about to say, well, now we've created these Skyrmions, we can move them around. This is in fact an older experiment. So here we've got 2 micron wires of a very similar multilayer, cobalt boron with iridium and platinum above and below it. But when we were doing these experiments, and again, it's all scanning X-ray microscopy, we didn't have this fancy injector structure. So what we did here was we applied a little bit stronger current pulses to just heat the wire, and then you would get a state where you can see all these patches of bright contrast. So you can fill the wire up with several Skyrmions sort of randomly thermally nucleated. And then we apply these weaker pulses, and we'd apply them in pairs, and after each pair we'd take an image. And that's what these colored points show you. So we could sort of track an individual skyrmion and see how it moved after these pairs of 9 nanosecond pulses. What you can see is they all move down the wire in the direction of the conventional current density, which shows you they're being moved by spin orbit torques. And they tend to drift to the right, so they don't move in a straight line with respect to the current. And they all kind of move in rather different ways. You can see that these tracks aren't all kind of uniform straight lines of the same length. Some skyrmions move further than others. The tracks are not necessarily always exactly straight. And we made measurements here at various different fields. So here we are, at 0. And these negative fields were intended to compress the skyrmion, reduce its diameter, because theories that describe this motion tell you that the motion should be diameter dependent. So you can see we acquired lots of data on lots of skyrmions, and then we have to sort of try and make sense of all that somehow. So I want to introduce this thing called the Skyrmion Hall angle. So as you just saw on the previous slide, the skyrmion doesn't move in the direction that the current pushes it. It tends to move at some angle. And the analogy that you make, this is Karen Evershaw-Sitter's picture, the analogy that you make is sort of with the Magnus force. So if I kick I'll call it a football, some people might call it a soccer ball. If you kick this thing and you get some spin on it, then there will be a Magnus force that pushes it in the transverse direction, and it will travel at some angle and even in a curved trajectory. And this is very useful for getting around the defensive wall when you're trying to score a goal from a free kick. So skyrmion, because of its chiral nature, similar thing happens. There's a transverse force that has some analogy with the Magnus force. What that means is that the current, it moves at an angle with respect to the current density. So this this blue arrow would be the direction of the current drive, and then this black arrow would be its velocity, and we would then define this angle and call it the Skyrmion Hall angle. I guess this was one of the main things we were interested in studying here. So in the previous slide, you saw there's clearly a Skyrmion Hall effect because of this sideways drift. So here we collected together all our data for all of these skyrmions as a function of diameter, and measured the Skyrmion Hall angle. And you can see, there's quite a bit of scatter here, but you can make out some things. So one is that this cloud of points isn't sort of symmetric about 0 angle. It's shifted up a little bit, and the average Skyrmion Hall angle of all of these skyrmions is around 9 degrees, but it doesn't really seem to depend very much on the diameter. Our smallest ones are less than 100 nanometers in size, and the largest ones are 700 or 800, and in between this looks pretty flat. Actually, in the paper we showed that this is actually kind of consistent with what you might expect for the particular material properties we have. On the other hand, if we take all our skyrmions and instead of sorting them out by diameter, sort them out by velocity, how fast they move in response to these current pulses, then you find something quite interesting, which is, of course, we still have the same average for the Skyrmion Hall angle because we haven't changed those values. It's still not about 9 degrees. But for our fastest skyrmions, traveling at maybe 10 meters per second or a bit more, there's only a smaller spread. Well, it's maybe 10 degrees either way, around that 9 degrees. Whereas at least, if we compare it to our slowest skyrmions that are only traveling at, 1 or 2 meters per second in response to these current pulses, then, the spread is enormous, and the Skyrmion Hall angle can basically be anything between plus and minus 90 degrees. So the way we sort of interpret that is these skyrmions are in kind of quite a lumpy energy landscape. a quite rugged landscape, and some of them are in regions where they're easily able to move in response to current pulses because the landscape is relatively flat there. So they will move quite fast, and they will tend to move with their intrinsic Skyrmion Hall angle. Whereas these Skyrmions down here are in some very rough and rugged part of the energy landscape. So when you kick them, they don't, with the current, they don't move too far, and they move probably in a direction that's mainly controlled by the gradients in that energy landscape. So that's the interpretation that we have for these data. So I want to finish off actually with an even slightly older experiment. So this was where we were trying to study the electrical detection of these Skyrmions. And so we made devices like this. So here we've got a disk, 1 micron diameter disk of Skyrmion material, platinum, cobalt, iridium multilayer, and attached to it are these leads. Everything is still on a membrane, and they're set up so that we can make a Hall measurement. The current flows this way. We've got voltage probes on either side. And again, everything is inside the microscope at the Swiss light source. And in those days, actually, the contrast wasn't kind of tweaked up to be quite so high, but I hope you can see the dark disk here of contrast that is the disk itself, and then there's a bright spot of the Skyrmion inside it. And you can apply a field to that, and it will compress it, and then eventually at this value of field, it will disappear. And this was set up so that we could make Hall measurements at every time we took an image, or the other way around. So for every Hall measurement, there's an image that shows you exactly which spin texture led to that Hall measurement. And you can see the Hall measurement kind of drifts down as we compress the Skyrmion, and the measured diameter in the image drifts down, and the digital magnetization derived from the image also kind of drifts up towards saturation. So we can take all those data points and try to analyze them. So if we look at this figure, it takes a little bit of explaining. This is the magnetization in the disk as determined from the image, normalized to the saturation value of 1. So we're close to saturation here. So this is sort of between plus 0.9 and 1. And then this is the normalized Hall signal compared to the saturation value, going from about minus 0.7 to around minus 1. So we've got this big cloud of points here. What we can do is re-bin them all and do some averaging, and then we kind of get this straight line with these black points are where the Skyrmion is present, so the winding number's 1, and then just before we saturate, there's this jump to the saturation value here with the Skyrmion number is 0. This grey dashed line has a slope of -1, and that's there because if these Skyrmions will also generate an anomalous Hall effect, and the simplest model of that would be to say, well, that's just proportional to the Z component of the magnetization, which is what the Stixon image is. And so if we had only a non-anomalous Hall effect, our data should lie on this line. As you can see, they lie on a line that's parallel to that, but it's offset by this amount. So that's studying just one single Skyrmion, and we can see there's a size-dependent part to the Hall signal, which is exactly what you would expect to get from the anomalous Hall effect. But there's this offset that seems to depend on the topology in the disk. What we did then was to measure more disks with different numbers of Skyrmions in them. These green data down here are the ones we just saw. And again, they all kind of lie parallel to this line with different offsets. And when you work out the offsets, that gives you these red data points here, which are more or less linear in the number of Skyrmions in the disk. And this negative number here is Skyrmions where the disk is magnetized in the opposite direction with their core. So -2 is something that's opposite to +2. So the slope of this line gives us this quantity 22 nano-ohm centimeters per skyrmion in the disk. This is way too large to be described by this conventional Berry phase theory, although there are other observations of these large signals. So it seems to require some new theoretical development to understand. I just want to quickly finish off by saying what we've been doing most recently is starting to look at synthetic antiferromagnets. So of course, we haven't had so much lab access in the last year or so as we might have liked, but we have been able to do some modeling. So as expected, we've done analytical and micromagnetic modeling. And we found that when you go to a synthetic antiferromagnet, your skyrmions are smaller than in the conventional ferromagnetic multilayers I've just shown you. They move faster in response to spin orbit torques. And also because in the synthetic antiferromagnet, there's no net topological charge. They move in a straight line. There's no Skyrmion Hall effect anymore. So now we're back in the lab. We're starting to make materials that might show us this physics. So here's an example. This is a perpendicularly magnetized synthetic antiferromagnet. There's a region here at zero field where we've got two out-of-plane layers that are coupled antiferromagnetically to one another. So there's no net magnetization. And we can look at expanding bubbles in these layers, and we can see there's a strong DMI. So now we're kind of pursuing this has all the right ingredients, and so now we're pursuing sort of imaging the kind of spin textures that we get in these kind of structures. So let me conclude then. We have nucleated single skyrmions in a controlled way. Actually, though I didn't show the time resolved data, we can see that happening with sub-nanosecond resolution. We've observed this propagation through this complex energy landscape, and we've measured their Hall signals, which you can split into a size-dependent part that comes from the anomalous Hall effect, how much reverse magnetization is inside the skyrmion. But there's also this size-independent part that seems to require some new theory. Either this Berry phase theory needs revamping for this new situation, or maybe there's some new mechanism there. Okay, thanks very much, everyone, for your attention.